So I'm going to be talking about voice over LTE and voice over Wi-Fi. I'm not sure if all of you are familiar with this terminology as such. LTE is nothing other than 4G. So I'm sure that most of you will have a 4G supported smartphone with you right now. And these are rather new protocols, and in most cases, you will be still making your phone calls via circuit switch networks, as he said before. It is not yet into 4G. But if you make a call and if you see that your LTE or 4G is not falling back to the symbol E, which is basically the circuit switch network, that basically means you don't have voice over LTE, but if you still see LTE there, then in most cases you are making a 4G call. But in that case, you need the SIM card with the 4G voice support, and also a phone that supports Wi-Fi calling or 4G calling support. So yeah, we will get into that later. So about me, my name is Priya Chalakal. You can call me Priya. I know it must be a very hard name. Actually, it's even longer, but I've made it Priya so that people can actually call my name kind of correctly. And I work at ERNW. It's a company in Heidelberg, and we do security consulting and penetration testing and so on. I likes to work with telecommunication security protocols. I also like PCAPs. I like looking at binaries. I like reversing protocols, and I kind of like everything in security in general. I completed my master's in March from TU Berlin and Unity in Trento. I have a blog, and I also write in the company blog, which is called insinuator.net. It's a very interesting blog, not just only my posts, but also posts from others in my company. So if you're interested in security, you should take a look at the blog. So today, I will give a very brief introduction about what is my talk going to be about and the protocols involved and so on. Then I will also talk a little bit more about the fundamentals. And then there is the first part, which is about attacking OpenIMS, which is an open source implementation of IMS. I will tell what is IMS and so on later. And also, it is without any IPsec protection in that. So, but we will just look into some interesting attacks there. And then we will get into the second part, where we are actually working with real telecom providers. And in there is IPsec already implemented. And then we will see how we can sniff, what kind of information can we get, can we really do some injection, and also finding some keys, which is used in IPsec, and so on. There is also a demo. Unfortunately, it's not a live demo, but that will be the most riskiest thing for me to do here, to use a German SIM and try to make a call, and I'm pretty sure it doesn't work. So I have it recorded, and then I will also propose some mitigation. So to start with, I like to give a brief introduction about how telephony evolved. So in the initial days, or even now, we have circuit switch networks. So most of your phone calls, starting from the old hard GSM Nokia phones, mobile phones, make use of circuit switch networks, and it's called PSTN. It's public switch telephone networks. And the idea here is that there is a dedicated channel made for making your call, unlike the packet switched, which doesn't require a dedicated channel. It roots back to 1876 when Alexander Graham Bell invented this telephone. And since then, we had analog initially, and then we moved to digital, and we still use circuit switched networks. And then there is this packet switched networks, which makes use of IP. Internet is the biggest example of packet switched networks, which makes use of TCP/IP as the protocol stack behind. And I'm sure that all of you must have used voice over IP, which is we have enough examples like Skype or WhatsApp call or Viber or so many other clients that supports voice over IP. But our talk is going to be about voice over LTE or voice over Wi-Fi. But this is closely related to voice over IP because in my talk, I'm not talking about anything at the radio layer or physical layer, but at the IP and the layers above. So it's pretty much the same. The protocols which I'm going to talk about is very similar to what we have in voice over IP. I will talk about that later in detail, but it's called Session Initiation Protocol, or SIP. So for those who are familiar with it, will know it already. Voice over LTE was introduced in South Korea in 2012. In Germany, it came only in 2015. Also, voice over Wi-Fi, I don't know when it came for the first time. I found multiple data that suggested different things, so I wasn't sure, but it's there since 2012 or before. But in Germany, it's released for the first time by Telecom in 2016, which means these are really new, and this hasn't been there since a very long time. So that also makes it very interesting to look into the security aspects of these protocols. Okay, yeah. So now let's get into some fundamentals. This can be a little bit boring, and I don't really want to put you to sleep right after lunch, but I will try my best to make this part short and interesting. So initially, we had GSM, or the 2G networks, as I was saying before, and this relies totally on the circuit switch networks, but we don't have anything to do with that right now. And it supports only voice or SMS, so your 2G phones never had any internet facility. And after that, there came GPRS. Don't ask me the full forms of these. I don't know. I don't remember. It's something radio, something like that. So it supports voice and SMS in the circuit switch networks. And then it was introduced packet switching also into GPRS, which mainly supported data. So you were able to access internet and do something with the internet. And then came UMTS, which is a little bit advanced 3G support. It had other network elements evolved, but the idea was pretty much the same. There were circuit switched network as well as packet switched networks in here. And then came 4G. So 4G is with the idea is that there is no circuit switching anymore. There is only packet switching. We don't need circuit switching in that. But 4G also supports voice over LTE. So you can make voice calls in 4G. But right now, most of the phones that you have is doing circuit switched fallback, which is called CSFP, which doesn't make the call via 4G, but just falls back to the PSTN, or the circuit switch networks before. So but in my talk, I'm going to be talking about VoLTE, and it's not about CSFP. So VoLTE is the one which is supporting SIP, or Session Initiation Protocol, which is similar to the voice over IP thing. Okay, so that's a very big overview of how evolved packet core is an integral part of LTE or 4G. Now, we see that there is 3GPP access technology here, and then also non-3GPP access technology here. So voice over LTE or VoLTE falls here because it makes use of the cell towers, which we see, and also the radio. So that's a 3GPP access technology. And voice over Wi-Fi or Wi-Fi calling falls in here because it makes use of the Wi-Fi and it doesn't require a mobile tower. But then we will see that the IMS, or IP multimedia system, so that's the main component which we are focusing for today. And that is common for both voice over Wi-Fi and voice over LTE. And there are other components involved as well, but it's not necessary to know all that in detail. This is how the voice over LTE stack would look like. So there are multiple protocols involved. eNode B is nothing other than the base station or the cellular tower. In 4G, it's called eNode B. In 3G, it was called Node B. And in GSM, it was called base station, simply base station. I'm sure that you must be familiar with something like a fake base station attack or an IMSI catcher. These are the usual telecommunication-related attacks. And in those cases, you have a fake base station here, and you try to do such kind of attacks. But in this talk, we are not focusing on such kind of attacks as well, but we are trying to attack IMS from these three layers. So it's IP or TCP, and also voice over IP. So by voice over IP, I mean SIP. So I'm saying this again and again, but this will come up later. So as I said before, it's the IP multimedia subsystem, or that component over there, which is the backend, which deals with all the IP-related functionalities. So it contains components called as call session control functions, which basically enables you to make a call via IP. So there is a server, there is a proxy, and this forward stuff. But yeah, the component architecture would look something like that. So that's your phone. And then you have the cellular tower. Then there is a gateway. And these are the call session control functions or the components in IMS. And HSS is nothing other than a database which contains all the identity information of the user. So whoever is a registered user with a SIM card, with a contract or something, all his information will be saved in here. Okay, so I was talking about SIP for a long time. So SIP is Session Initiation Protocol. This is basically used for signaling to IMS. So by meaning signaling, I mean that all the activities that happen before you make a call. So whom are you calling, who is calling, and this kind of information falls under signaling. And the IMS signaling is done by SIP. And it's a protocol very similar to HTTP. So it's a text-based protocol, and it also doesn't matter which transport protocol it uses. It works with TCP as well as UDP. And it also contains another protocol called SDP, which is Session Description Protocol. So this basically describes the multimedia session which is going to happen. So what audio type or what video type are we going to use, or what are the support in this particular phone or not. So this is the basic flow structure of SIP. So there is something called invite packet, which basically means you are making a call. And then you see trying messages coming back, and this ringing message coming back. That ringing message is actually when you hear that ringing sound when you make a call. So this whole part in the front, this is the signaling part. And this is not charged. This is something which is happening just before you make a call. And this media session part is actually when you're talking. So that's when you start getting charged. So, well, yeah, as I mentioned that because in later section we see that we try to send information in this part for free, so sending free SMS or free calls. Not getting charged by sending via media sessions. So yeah. So as I said before, SIP would look like that. So as I said, it's a text-based protocol, just like HTTP. Like HTTP post or get, you have something like invite or options or register or keywords like that. There are multiple varieties. Then you see from and to. Also, if you're making a call from your phone, it will be your phone number there, and also the to phone number. And yeah, there is also other information about your phone and mode, different modes that could be used, and so on. And this part is called Session Description Protocol, but we are mainly focusing here, also for one attack, we are going here, but yeah. So okay, I'm done with the fundamentals part. Now comes the more interesting part. I hope you all got a brief overview about what kind of protocols we are going to deal with here, and what are we actually talking about here. It's about 4G and the different components involved and so on. So the main requirements for the first part of attacks involves OpenIMS. OpenIMS is an open source implementation of IMS. So IMS is the IP multimedia subsystem or the backend. And so all the attacks in here is more like a simulated attack. So it's not done on a real provider, but I made up my backend with OpenIMS, and I'm trying to inject stuff and so on. But this is still relevant because this particular OpenIMS is based on 3GPP specifications, so it follows all the specifications right. So a provider who is implementing simply based on these can have these kind of issues unless they don't fix it. I also use something called ViProi toolkit. So that's a metasploitable framework which is specifically for voice over IP. So you can do some fuzzing or some injection attacks and so on with ViProi. And I also use some IMS clients, but that's not important. This is how the SIP proxy tool would look like. That's your phone, and you can forward that to a particular proxy. You can do the injection here and send that to the server and get back the information from the server. You can look that in here and send it back. And this is the open source OpenIMS, which I said before, the open source implementation of IMS. This contains all the components important for IMS. So I was talking about PCS. These are call session control functions that handles the calling functionality. So you will see all those components in there. So it's already implemented, and I could simply use it. So how is it related to VoLTE and voice over Wi-Fi? Because both of that make use of SIP. So very similar to OpenIMS protocols. And as I said before, this is experimental, and it is done with desktop clients, not really mobile clients. But at the network layer, it's all the same. And we are mainly going to do some SIP header injection attacks. So we are going to tamper with the different header fields in SIP and see what can be achieved. And there is no IPsec in this. So in this part of the attacks, we don't have any IPsec involved. And both the attacker and the victim is a registered user. So both of them have an account in the OpenIMS. So the first attack is MSRP fuzzing. MSRP is also a part of the signaling protocol of SIP. MSRP is called Message Session Relay Protocol. So I made use of the ViProi toolkit, which is the Metasploit framework here. So it was a pretty easy one. There was a particular header, and if you just simply fuzz the input to a long input string and send that using the proxy tool, which I mentioned before, it crashes the receiver at the other end. So I make a call to someone, and I'm able to crash the receiver's client on the other side. And what it implies is that there is the IMS or the client didn't perform any kind of input validation in the header fields of SIP or MSRP that led to the crash. So you can see that, there is a very long, so this is the SIP message which was sent. And in that particular header, a file selector name, I sent a very long string. And this is the client which was there on the other side, and it says client has stopped working. So that was the first attack. Okay, now moving on to the next attack. So first we saw that fuzzing is possible. We can try to fuzz with the header values. The second type of attack is location manipulation. So there is a particular header called p-access network info in SIP, and this defines the user location in the access network. And these are the country, so MNC, mobile network code or mobile country code, local area code or cell identifier. These are values, just integer values, which basically tells you which country are you located in, which particular local area code do you have, and which particular cell ID are you connected to? So which mobile tower are you connected to? So yeah, this basically contains your particular location, and an attacker can send an invite request, yeah, to Alice, which is a victim on the other side with a crafted location. And so during the initial registration process of every SIM card, this particular value is checked if it's right or wrong. But then later, if an attacker modifies this, that is still accepted, and it's not checked or rechecked to see if it's the same as during registration or not. So this is not about privacy, so someone else is not getting your location, but you can basically change your location in case if you need to evade any lawful interception techniques. So yeah. That was yeah, the second attack. Now, there is another particular header called Visitor Network ID in SIP. In this particular header, this is not supposed to be sent from the user end. This particular header should be added only by the access network or the cellular tower, which gets your first packet, and this header is appended by the access network. But an attacker from the user end itself can try to add this header and send with a malicious value, and that is still accepted at the other end. So basically, you can try to make your roaming calls as a local call if you change the access net, if you know the access network name of a local provider. And yeah, we see that the fake value is still there as appended by the attacker, and the original value is only appended on the end. This should be removed, actually, and not appended like this. And also, SIP protocol is, so that was the third attack, and this is the fourth attack. SIP is a extensible protocol, so you can simply add additional headers. So there is this particular header called X header, which you can use for adding additional information. So you can send messages for free, like that, without the actual media beginning at all. There are also a lot more attacks possible. So even in OpenIMS, spoofing works. So there was no, you could simply change your phone number to someone else's phone number. So the receiver would think someone else is calling you and doesn't reveal your identity. You could do other injection, XML or SQL injections, and there is also a possibility of trying out denial of service and also fuzzing. We already saw some fuzzing. So to summarize the first part of attacks, so we already saw an MSRP fuzzing attack. Then we saw a user is able to manipulate the location of the user itself. Then we saw another attack where he can change the access network information and make a roaming call a local call. Or you can send secret messages via X header, which is extra header field injection attacks. So these are man-in-the attacks, end attacks. So a registered user itself is the attacker. There is no man in the middle as such. And all these did not have IPsec. So we did all these attacks without any IPsec. So this is bad from the provider's perspective. So a provider doesn't want a user to make free calls or changing roaming to local or do fuzzing or stuff like that. So how do we prevent such tampering or SIP on the SIP header fields? So, well, one solution could be to bring integrity protection. So you add something like a hash value in the end, which calculates the hash of all the SIP headers from the user end itself, so that an attacker is not able to inject and protect the keys. So that's basically what IPsec does, or something like TLS, but yeah, mostly in all the telecommunication providers, you will find IPsec in use. And so, yeah, this is the most interesting part. Can we actually mess with the real providers that we have right now or not? So that's where my second part of tests begin. That's attacking the telecommunication providers. So till now, we just only had OpenIMS, which is an open source implementation of IMS. So I simulated the backend, and I was trying to inject stuff and identify some issues. Now I'm going to play with the real SIM cards of providers and trying to see what kind of information can I get. So there are some requirements for the second part of tests. So I used a device called SimTrace, which is from Sysmocom. It's a very interesting and nice tool to play with if some of you is interested. It allows you to sniff the communication between the SIM card and your phone. Yeah, we will see later why this is interesting. Then you also need VoLTE or voice over Wi-Fi enabled SIM cards. So you have to have the contract with VoLTE support. So not every SIM card is VoLTE enabled by nature. And then you also have to compile Wireshark with gcrypt, which is which supports all the IPsec libraries necessary for decrypting all the Wireshark PCAPs. So the interesting interfaces here, which might be interesting to look at, is called as RMNet 0 or RMNet 1. So these are interfaces just similar to WLAN 0 or ETH 0 as you see in your if config. But if you go to an ADB shell and if you look in there with a VoLTE enabled phone, you will find additional interfaces like RMNet 0 or RMNet 1. For voice over Wi-Fi, you simply listen at WLAN 0, but I also found one additional hidden interface there. I will also talk about that later. And then I'm also looking at the SimTrace hardware, which I was talking about before. With that, I can also look into the iSIM interface in the SIM. So there is also a communication with the SIM card, and yeah, we will see what we can find there. So there is also IPsec in here. So previously we didn't have any IPsec, and we were only focusing on the SIP header injection field. But now we also have to look into how to overcome the IPsec layer involved. So the protocol which is a part of the IPsec is called ESP, or Encapsulation Security Protocol, which is there for both voice over LTE and voice over Wi-Fi case. And we will see that there is integrity protection in VoLTE and voice over Wi-Fi, and also encryption in voice over Wi-Fi. These are some details, but yeah, the main idea is that there is IPsec and there is integrity protection in each and every packet that gets sent. So it would look something like that. It's all IPv6. I hate to see IP addresses so big, but yeah, it's all ESP, and yeah, probably the bigger bytes are the packets with the SIP or the signaling protocols inside. And so the first part of tests was just sniffing at these interfaces which I mentioned before. So previously we were able to, so as I said, there is RMNet 1 or RMNet 0 for voice over LTE. And for voice over Wi-Fi, these are the interface names which I listen to. And this is a simple trick which you can use for actually sniffing with Wireshark itself. You can just do ADB shell and go to the Android shell, and then do TCP dump on this particular interface, and forward that with the Netcat listener. And from your laptop, you can simply do an ADB forward in that port, and you will be able to listen with Wireshark. So yeah, you can simply straightforwardly use this to listen on this interface. So in the phone, I was, in case of voice over LTE, this was my interested interface. And for voice over Wi-Fi, I looked at both, But in WLAN 0, you will see that it's more like an IPsec tunnel, so like a VPN tunnel. So you will see only encrypted communication in there. But then there was another interface called EPDG, which contained the exact same traffic as in WLAN 0, but before encryption. So I was simply able to listen to that with this kind of setup. So instead of ARMnet 1 there, I use EPDG. And I was able to find non-encrypted traffic. Yeah, so as I said before, there are some observations. So in case of voice over LTE, there was no encryption at all. So I was able to see all the traffic in plain text. But there was integrity protection, of course. So I couldn't do injection. Or if I want to change any value in there, I should have the IPsec key, which I don't have. In case of voice over Wi-Fi, there's already encryption. But then I found a hidden interface with non-encrypted traffic. So I could still see all the SIP traffic, which is not encrypted. So it looked somewhat like that. So this is not an emulated or simulated environment like with OpenIMS. This is with a real provider listening to a VoLTE traffic or voice over Wi-Fi traffic. So there is the phone number and yeah, the provider name and yeah, this is the header. You know, P access network info was in one of the attacks before, and then there is IMEI number, and there is also the to and from address and the phone numbers in here. Yeah, these are the IP addresses. So this is how there were some information disclosures. So as I said before, I was able to see that there is IMEI numbers of the person who is sending the information. Then utrans cell ID is the location information. So this is in the particular header called P access network info. So for voice over LTE, it would look like that. I changed these values to some garbage, but yeah. In case of voice over Wi-Fi, it is called IWLAN node ID, and you will still find particular node which you are connected to. So yeah, when there is an incoming call coming, you are able to see the IMEI number of the person who is calling you, and that's cool, right? You get the private identity of the person who is calling you. And what was even worse is that I was also able to get the IMSI. So IMSI or IMSI is the private identity of the SIM card of the person who's calling you. So that's even used for authentication. So if you are able to get the IMSI value of another person, it simply means you can have well, it is still hard, but it's not so as easy and straightforward, but you could do some attacks for doing all the identity theft of using another person's identity to make whatever you need. So IMSI is like the authentication value or the private identity of a SIM card, and leaking that is pretty bad, and I could see that as well. And then some private IP of the IMS. I don't know what to do with that, but I still found that. Yeah. Okay, so that was the first part. So first part was just listening, simply sniffing at the various voice over LTE or voice over Wi-Fi interfaces and see what kind of information do you have there. And I saw that there is IMSI values and IMEI values and so on. And there was no encryption in case of voice over LTE at all. And in case of voice over Wi-Fi, there was encryption in the WLAN or the IPsec tunnel. But then there was a hidden channel, which is called EPDG, which contained non-encrypted traffic, and that allowed me to look at all the SIP traffic without encryption. Now, okay, I still cannot do any injection attacks because there is an integrity value in each packet that is sent, which is the hash of the whole headers, like the SIP headers, which is used. So I need the IPsec key if I want to do some kind of injection or tampering with the SIP header fields. So that's where the hardware called the SIM trace, the SIM tracer hardware becomes very interesting. I use this particular hardware device. So that's a Samsung S7 phone, and I had to put this. This is the SIM trace hardware, and I had to put in the SIM slot of the phone. I inserted the SIM trace, and in the SIM trace hardware, I put the SIM card, and I connected the SIM trace to my laptop. So basically, it's like a man-in-the-middle setup between the SIM card and your laptop. So no, between the server, yeah, of course. Okay, so one interesting protocol here, which is used for authentication, is called EAP-AKA. It simply means authentication and key agreement. So the key which is used for IPsec is agreed between the SIM card and the provider using this particular protocol. This protocol is easy. There is nothing hard to understand. So this server would send you a challenge and also an authentication value, which is called RAND and AUTN. So RAND is a random challenge, and AUTN is the authentication value of the server. And on the SIM card is having a pre-shared key, which is secret information, could be an algorithm as well. It's called the AKA algorithm. So based on the values which is sent by the server, it would perform the algorithm and derive the session keys and also a response. So this RES is the response to the challenge that was sent. Okay, and send back the response to the authenticator. And yeah, I mean, if the RES value which is calculated is right, then yeah, the authentication is done. So EAP aka protocol works like that. And basically, with the hardware called the SIM trace, I was able to find this particular calculation of the session key, which is happening between the SIM card. So I was able to see these kind of very interesting information, which is used in IPsec using the SIM trace hardware. So basically, I was able to get the integrity key and also the ciphering key, which are the keys used in encryption. So to make life easy for me, I wrote a Wireshark dissector, which would basically parse the whole information from the SIM trace hardware and will show me in Wireshark. So I was able to get so CK and IK are the keys. And I also did a validation if this particular key itself is the key which is used for integrity protection. So I try to provide the key. When, yeah, it shows here that it's correct. Yeah. So I was able to validate that the authentication is also successful with this particular key, which I got from the SIM trace hardware. Now, this basically means that I can do all the injection attacks which I was doing in OpenIMS before. So IPsec didn't solve any particular issues. And to summarize the second part of attacks, we saw that there are some information, important information, like the identity information that gets leaked. And then sniffing the iSIM interface of the SIM card using the SIM trace hardware, I was able to get all the IPsec keys, which was used. Okay, so I will show a simple demo to give an idea of how this injection and the whole thing works. So I'm opening an ADB shell, and I need root privilege as well, because I want to listen to all the interfaces. As I said before, you will see that there is RMnet0 here, and that's the interface which is associated with the VoLTE or voice or LTE interface. And now I am simply doing a TCP dump, so I want to listen to that particular IP. And for forwarding that, I can use ADB forward. So from my laptop, I'm trying to just listen to the traffic with ADB forward. We already have some packets there. I'm trying to look at only the zip packets. I already see some zip packets. So now I'm sending a message from my phone to see that how this would look like in the Wireshark, how the packets would look like, and if it's sent via zip itself or not. And I see that there is a zip invite message there. And if I simply do a TCP stream, I can see all the zip packets, which I was mentioning before. There is the phone number. So that whole part, yeah, that is the phone number. I think there is also the location information of the user. Yeah, that particular header, it's p-access network info. I couldn't make this bigger because it's Wireshark. I'm really sorry. Okay. It's also nice that it's not seen. There is also IMEI and IMC values there. So, okay, so that's the message which I'm sending in here. It's just he. And now I'm trying to do a replay attack. So that's a very simple attack which I'm trying to do. And I'm opening burp and also a SOCAT listener in my phone. So I'm changing the value to something else. And yeah, that is my phone's listener. So I open another ADB shell and open a SOCAT listener in there. And yeah, so my laptop and my phone is connected to the same Wi-Fi network. So that's how I am able to send the traffic from SOCAT and burp. Yeah, I open a listener and send that to my phone. And that particular IP which I'm showing there is the server IP. So I need to specify that in the SOCAT so that the message is redirected to the IMS server. Initially, I won't get any proper reply from the server. That's because there are some values. So I only got a trying reply. But that means I didn't get a 200 OK, which means the message got sent or it became successful. But I had to change some specific ID values. So I just had to increment those values. So there are some values called call ID. So you will see that I'm changing those values in there. Yeah, that's called call ID and yeah, some other session values. Just increment that to the next value. And well, yeah, after that I got, that's 183 session in progress and a 200 OK. Oops, sorry. Yeah, a 200 OK, which basically means that the IMS server of the telecom provider send me a reply. Yeah, OK, so that's it. That was a simple, yeah. So, yeah, so to summarize the whole thing, so in the current implementations of voice over LTE and voice over Wi-Fi, it makes use of IPsec. We looked at some injection attacks on OpenIMS. The next step would be to try out those kind of injection attacks. And also we extracted the integrity key and also the ciphering key, which is used in IPsec. So we simply can do all the injection attacks and reproduce these attacks. To propose some mitigation Never rely on the user end security. So having an IPsec on the user side doesn't, the key is also with the user. So you can always do injection attacks. Yeah, never rely on obscurity. Even if the key is somewhere hidden or only calculated within the SIM card, it's quite easy to get that and produce your own packets. So the protection should be always on the server side. There should be traffic monitoring and also apply whitelist rules on each and every SIP header fields to see if there is fuzzing going on or if there is a change or cross validations with the servers. And also there should be encryption. So in VoLTE LTE, we saw that there is no encryption at all. But if there is something like a fake base station or something, they might be able to see IMSI values and IMEI values. So encryption always helps. Yeah, that's not important. OK, so that's it. If you have any questions.
Thank you very much. We do have a short moment for one or two very quick questions. Yes?
Hi, thank you for a very interesting talk. My question is, would have using SIP over TLS have mitigated some of these attacks? Because I work for a company, we do voice over IP soft switches, and what we see is that most of our customers do not use SIP over TLS, so they use unencrypted connections. And also for the multimedia part, so they use not set RTP, but plain RTP.
Yeah,
and I really wonder whether this is also a client problem. I don't know, because it's hard to say, but
no,
we just don't see it.
Even if it's SIP over TLS, the certificate is on the client side, right? So the attacker is the user itself. It's not a man in the middle attack. The attack is coming from the client side itself. So the security cannot be based on the client side or this transportation layer security, but it has to be whitelist rules or protection on the server side to prevent things like injection attacks. Even if it's TLS, I think we can do the same thing, right? And also, yeah, I don't know how it would work with the, yeah, I think it's still possible with even if it's TLS.